I'll get going then. I'm Dominic Bloom, Applications Engineer at iCOMAT, and I've prepared a short presentation today that I'll take you through. First of all, I want to introduce the company and what we do. Then I'll talk to you about some of the applications that we're working on, so where our technology can be used. And I think there's some time for questions at the end. So the iCOMAT story. As Carwyn said, we are a University of Bristol spin-out, and the company was incorporated in 2019, so relatively new. But already we've grown to a team of 11, and we are currently recruiting for 3 new positions. So if you like what you see, then please do feel free to check it out. We currently have 7 live projects or contracts that we're working on, so we're pretty busy at the moment, and I hope to be able to share some of that with you. And I should probably have started with this, but iCOMAT is a machine builder, and we have developed the world's first automated fiber placement machine, automated tape laying machine that can place tapes along steered paths. And this is a patented technology, and that's what we do in a nutshell. I need to, there we go. So the aerospace and automotive industries are really facing a lot of pressure to get the weight out of structures, and particularly in aeronautics, composites are really widespread, as you probably know. But even so, there is a need to get the weight of structures down even further due to the economic and environmental pressures. So yeah, composites are used extensively across the airframe, but we're reaching the limit of what can be done with existing technology. So there's a bit of a need for a step change there. And that's where we believe we fit in. Similarly for automotive, as electrification and autonomous vehicles progress, the weight of the body structure seems to be going up, which is counterproductive. And composites are clearly an answer to this, but there are some really important limitations in terms of cost and rate of existing processes, which means that they can't really be adopted for the automotive industry. So how are composites used at the moment? That's part of the issue. Composites, as you know, are anisotropic, so they're extremely strong in the fiber direction, strong and stiff, not so much in the transverse and through thickness directions. So the way we use them at the moment is we stack layers of straight fibers to form laminates which have roughly the same properties in every direction. Whilst this works and it's really good, it's by no means the most optimized way of using composites. So what we're proposing here is that if you use fiber steering and curved composites, you can really align the fibers with the load paths in your structure, and that way get the most optimized structure possible. Current technology, so I mean AFP and ATL, so automated fiber placement and automated tape laying machines, are the state of the art, and they're really good at placing fibers quickly in straight lines. They're great at that. However, if we want to utilize the benefits of curved fibers that I just showed you before, they're not so great at that. So the way they do it, these machines are normally robot mounted or gantry mounted, and the way they steer is they rotate the placement head to steer the fibers, but this causes bending in the tapes. And with bending comes defects such as wrinkling or buckling, which really have an important knockdown on structural performance. Our technology, so RTS, rapid toe shearing, is a fundamentally different way of doing things. So we apply shear to the tape and not bending, so you can end up with steering without any defects, and it looks a bit like this. So again, to come back, AFP and ATL bend the tapes, which causes defects. And it also, there's really a limitation on the width of the tapes that you can use with AFP and ATL. And the wider the tape, the harder it becomes to steer. So this is where the concept of minimum steering radius comes from. And that's traditionally around 500 millimeters to a meter for AFP. And that's the minimum radius that can be steered without defects. And as the tape width increases, that minimum steering radius increases as well. However, with rapid toe shearing, iCOMAT's technology, because it's shearing and not bending the tapes, we are able to steer around really, really tight radii, as low as 50 millimeters. So that's an order of magnitude improvement compared to the state of the art. Another point is, again, because we're shearing, there is no limitation to the width of tape that can be used. So our current machine is set up to work with tapes up to 100 millimeters wide, which is pretty wide for this kind of thing. Another point is, with the existing technology, when you try to place tapes side by side onto a surface, curved tapes that is, you inevitably end up with features like toe gaps and overlaps, which are pretty much unavoidable. But with iCOMAT's technology, because we're shearing, we are able to passively change the width of the tape as we deposit it. So the width increases or decreases, and that's coupled with a thickness increase or decrease. It's a little bit difficult to explain. I'll try again later on. But what that means is that we can place curved tapes next to each other and cover a full surface without any gaps or overlaps. So we like to class the benefits into two categories. One is the advanced structural efficiency, so where we target the optimized designs in order to reduce the amount of material needed. And we typically say that can be in the order of 10 to 30%. The other area where we can bring benefits is parts with high geometrical complexity, and to manufacture shapes that were not possible to make with state-of-the-art technology. The example I give here is a really curved fuselage frame, which can be made in theory using toe shearing, whereas the traditional approach might require discontinuities or many segments to be joined together. Now I'll talk to you about some more specific applications and improvements. So if you look at the right-hand side of the screen, this is a wing cover, and the images I show you here are from an independent study at the University of Bath that looked at how this structure can be optimized for buckling behavior. And it was shown that with if you enable a really steered design, such as that, which can be made with CTS or RTS, you can get the weight of the structure down by almost 40%. And that's because of the minimum steering radius constraints. Whereas with AFP, you could only achieve under 10% weight saving. And on the left-hand side of the screen, this is actually a project which is running at the moment with Airbus, BAE, and the National Composite Centre, where we're looking at manufacturing a panel with a hole in the middle or a discontinuity. And this could be, it's representative of a lower wing skin with a manhole or access port, or a window frame in a fuselage. But what we are doing in this project is showing how we can optimize the structure. And we're about to manufacture a demonstrator panel, which is only 8 plies thick, but is able to have the same performance as the 24 ply thick baseline when considering the tension load case. So it's a really significant improvement and reduction in composite material used. Another benefit that we can enable is aeroelasticity. So what do I mean by that? Well, to make this kind of aeroelastic design, you really need to be able to tailor the fiber laminate and steer the fibers in plane. And what's been shown already in the wind tunnel is that the steered design has significant improvements compared to the traditional UD design. Specifically, it's got significantly lower deflection under load in the wind tunnel, and also the optimized design is able to keep the angle of attack constant under load, and this has a really drastic improvement on the flight dynamics of the aircraft. Another thing that happens when you steer the fibers and tailor the load paths is that you can more uniformly stress the wing. You can move away stress concentrations from joints, for example, and spread them across the laminate, so you're using more of the composite. And this is an area which we are currently looking into together with the Ministry of Defence, where we have a contract. This is a bit of a new application here. We are working with the European Space Agency to look at these thin-walled cylindrical shells, which are typical for a launch vehicle. Now, these shells are really sensitive to geometric imperfections and buckling. So the current approach is to stiffen them with T-stringers or similar. What we are proposing is, thanks to this shear thickness coupling that I mentioned earlier, is that if we steer the fibers on this structure, we can get a thickness increase locally as that happens, and therefore create integrally stiffened structures. So we can stiffen the structure, make it thicker locally without adding extra material, which is a bit of a new concept. And we are about to manufacture one of these cylinders for the European Space Agency, and we'll send it off to be tested. So hopefully that's given you an idea of what we can do. I wanted to show you the slides with the industries that we're targeting, and then some of the applications where we think we can bring a benefit. And some of these I've already covered, other ones we're also working on, but by all means we're up for a discussion here. So if you think of anything that's worth looking into, we'd love to hear about that. So for aerostructures, these curved fuselage frames, also fan blades. Then for automotive, particularly, cars are full of these curved pillars and reinforcements. So that's a really interesting area for us. And then energy, of course. So I've left this slide till last because it's an area that I'm really interested in. It's close to my heart, and that is the benefits that we can bring to forming. And this started off with an automotive customer a while ago. They came to us and said, "Can you make this curved beam?" Because when we try to make it from straight fibers and forming, we end up with wrinkles. So that's the first thing we tried, and indeed you do get a lot of wrinkles, as you can imagine. So we then made an equivalent layup with curved fibers and formed it using diaphragm forming, and the results were vastly improved. And you can see in the picture that there were pretty much no wrinkles on that part. So that was 8 plies of 090. And that's really prompted us to look into rapid toe shearing and forming as a way of delivering a means to make 3D structures from 2D blanks. So we're currently scoping a project together with Solvay, where we hope to use their double diaphragm forming line, which is a fully automated forming line that they have to make an end-to-end demonstration. So we'd start at one end with a flat blank, and at the other end we'd have a fully formed, fully cured component. And obviously a key element of this is being able to use simulation to find out what the best paths are for forming. So we take the 3D shape, consider this hemisphere here as an example. We would virtually flatten that. And what you can see is when you do that, there's a, clearly you need to have fiber steering capability because the composite is curved. So yeah, we'd virtually unform it, then work out what the paths need to be, deposit that as a flat preform, and then form it. That's more or less what we're planning to do, and I think that's a really interesting application. Yeah, I'll keep you up to date with that. I wanted to show you this picture of our current prototype. This is the alpha version of the head, and it is in our Bristol facility, and it's really starting to look like a proper industrial machine, and we're really proud of that. I wanted to show you a video as well of the machine in action. Hopefully it's smooth, not too jumpy. I'll play that again and talk over it, if that's okay. Yeah, so here we are. This is a real-time video. We're depositing at around 0.3 meters per second. And we're using 100mm wide tape. And this is just a generic geometry to show off our capabilities. And yeah, it looks really good. It's got a minimum steering radius of 100mm, that one, I think. And a maximum shear angle of around 30 or 40 degrees. And just wanted to finish with some close-ups of the paths that we lay up. Really, they look really good, and no defects are observable. Okay, that was all I had to present today. These are my contact details, so feel free to get in touch if you want to discuss further. And I think there's some time for questions now.
That's great. Thank you for that presentation, Dominic. That was really interesting. Anyone has got any questions, please feel free to ask them. And I'm sure Dominic will try and answer them.
Can I start off with what I hope should be a relatively simple question to answer? I've always been fascinated by this, but there's something in my mind that tells me you can't continuously keep on steering a toe round and round in a circle if it's coming from a continuous tape. Do you have to have some sort of balance between left steer and right steer in each continuous length?
That's a good question. But you're absolutely right. We can't do a continuous circle. A lot of people have asked that, and there's some fairly fundamental reasons why that won't work. But to ask about the balance of left steer and right steer, it may be better if we take that one offline, and I can get some input from the technical team to support on that.
Sure. Okay.
Can I add a comment on this, Dominic?
Please.
Just from my point of view, what we are seeing with this technology is as you shear the material, it gets thicker. And theoretically, if you sheared it by 90 degrees, of course, it will get infinitely thick. So that's really a limitation in the same way as there's a draping limitation on standard materials. We have a limit on the angle as well as the radius that we can steer something. And what we're trying to do is get software which will recognize that and make sure that things can be designed which fulfill all those manufacturing restrictions.
That's exactly right. Thanks, Andy. The tapes that we share, they have a locking limit, so a maximum angle that they can be steered to. And that's a material property that can be measured and characterized.
It's interesting you talk about, as you shear, you increase the thickness. Does that mean then that you could imagine a cone? It doesn't have to be a pointed cone, it can be a truncated cone. Typically, the problems you have is that the circumference at one end is much larger than at the other, so you can't lay parallel tapes down the outside of a cone because it just doesn't fit. So can you toe shear to make them thinner as you go down the length of the cone then?
Yeah.
So you don't get overlapping.
That's exactly right. Yeah, we've got this coupling between the thickness and the width. That means we can do just that. We can place tapes side by side over complex geometry. Yeah, the issue is at the moment that's quite something new to get your head around. And as Andy will tell you, that isn't exactly incorporated into current design practices. So we're working on that. We need to be able to make this accessible to people so that they can design with it and make this kind of structure.
It's very interesting because it's something I've always been interested in because it's one of the limitations of parallel fiber composites, and it has a lot of applications, in particular in oil and gas industry, where you want to reduce the diameter of a pipe. You do that by the same kind of process, and normally you'd have to either do it by a filament winding process or just accept that you're going to get gaps and overlaps.
Anyone have any more questions for Dominic?
Dominic, how does the deposition rates compare with competitor capability that probably can't do what you do?
Yes, that's a good question. So during steering, we are much faster. So as I understand it, when an AFP machine has to steer around a tight radius, if it can be done, then it has to be done very slowly. So we are quite a bit faster. In a straight line at the moment, we're probably a bit behind in terms of linear speed, but there's no fundamental reason why we couldn't catch up. There's a fair deal of material optimization that can be done to get the parameters to allow us to travel a lot faster. I showed you that video we were working at 0.3 meters a second, but we've already done some trials which suggest that we can go a bit faster than that.
Okay.
Is everything you've done so far with thermoset resin systems, and do you think that it will be equally applicable to thermoplastics?
I was just about to ask that.
Sorry, David, got in there before you.
Yeah. So we've tried a bit of everything. We can do pre-preg, no problem. So that's thermoset pre-preg. We can do dry fiber, and in fact we prefer dry fiber because if there's no resin there, it's shear rate insensitive, so we can go a lot faster. The issue with thermoplastics in thermoplastic pre-preg is that you need quite a very high temperature to process them, and our heating system isn't really capable at the moment to handle that. But what we have done with thermoplastics is we've used commingled tapes, so it behaves like a dry fiber at room temperature, so we can shear it no problem. But then that needs maybe a secondary process to apply the heat and the pressure to get the compaction and consolidation you need. So these are things we're all looking into, and it's really customer driven. If somebody wants to use thermoplastics, then we're going to have to look at that more closely.
I think it'll be very beneficial if you could have it to work for thermoplastics as well. That actually brings me on to another question I had. Can you use different fibers? Have you just used carbon fiber, or does it apply for glass fiber composites? And can you use hybrid fiber composites, hybrid fiber materials like carbon aramid or carbon and glass fiber together in the same tape?
Yep. So we've tried it for carbon. We've tried it for glass. The only hybrid I'm aware of is this commingled format that I've talked to you about. So that's polyamide fibers mixed in with carbon fibers. There's no reason fundamentally why we couldn't process the hybrids you just talked about.
Does anyone have any other questions for Dominic?
What's the next steps in terms of industrialization?
Yeah. So our current core focus is to get this 2D capable machine ready for the market. And the earliest application that we're working with suggests that we'd be ready by 2022 for that particular application. Okay. Beyond that, we'd be looking at how we can integrate ability to do complex shapes. So this forming thing is really critical because you can keep your high deposition speeds by laying down in 2D, and then you can achieve your 3D complexity by a forming step. That's great, but inevitably people are asking for direct to 3D deposition, and that's a substantial package of work which we're undertaking in parallel. So the 3D machine, it will come, but it's probably something for the future, for the near future. Mm-hmm.
Okay, thank you, Dominic.
I do have a question in terms of the costs. A lot of the costs with an AFP obviously are getting the material slit into a narrow web format. How does the cost compare with this in terms of, have you done any cost analysis to show the difference between this technology versus an AFP?
We have actually. We have done that, and we've shown for this particular application that using a like-for-like material, because we're using wider tapes, that's less slitting. Mm-hmm. So you can save, I think it was around 10% like that. But then where the real cost savings come in is if you go even wider and even thicker, so way beyond what AFP can do, you increase your deposition rate and you can also reduce your material cost. And the analysis suggests that that can be around 40% reduction compared to AFP.
Yeah, thank you.
Have you looked at properties of composites like the mode 1, mode 2 fracture toughness to see if having opposite steered fibers at the interface of a crack improves the fracture toughness at all?
Yeah, that's a good one. Very specific. We are currently running a project which does look at the mechanical characterization of these laminates. The issue is that not all ASTM standards can cope with curved fibers. So straight fibers, no problem, but when they're curved, you start to get loading in secondary directions and so on. Mm-hmm. So there's a bit of work happening at the moment to look into that and how we test.
Yeah, that leads on to another question I was going to ask, and that's, do you see the need for additional standards to be developed to cope with these materials? So if you take a toe steered laminate and you cut it into a rectangular coupon, you're going to have chopped fibers, which can affect the mechanical properties. So how do you compare, for example, the tensile modulus with a unidirectional or a cross-plied laminate?
Yeah, that's what we need to look into, and that some of the tests may be applicable, and you can use them for curved fibers and sheared fibers. Some of them will need some development from scratch, and we really need to look to institutes like TWI and the likes to help us out with that, because that's expertise that we don't have at iCOMAT. We want to focus on building the machines, but we fully appreciate that the whole ecosystem needs to be brought up to speed. So ability to design, ability to analyze, and ability to test these materials.
So if you actually have a test specimen which has got a radius on the fibers going through it, of course, your first thing when you load it up is the fibers are going to try and straighten, and that creates transverse stresses which can cause failures, a bit like opening failures on an L section. So we are looking at failure behavior on these materials as well. So yes, it's an interesting area to look at in the future, in the near future.
There's something else that sparks an interest in me, and that's electrical properties of composites with carbon fibers, electrically conducting carbon fibers. You now have the ability to play tunes with the relative orientation of fibers in different layers, rather than just sticking to fixed angles. So you can, in theory, now start to target where various electrical processes take place within the laminate, which could have interesting applications.
Gosh, I hadn't even thought of that. It's yeah, that's a really interesting point, actually.
So if I jump in here, I think it's electrical properties and also thermal properties. So actually, quite recently we found a patent by Boeing, which is trying to use fiber steering and encode our process for satellite panels, so that you can control how the heat is dissipated in the structure. And another potential application is, PCBs for space, where matrix cracking is a problem because they see such a wide range of temperatures. I think these are all interesting applications, and nobody has really investigated this. There are not publications, and it's this one patent from Boeing that we found out. But yeah, so if you're interested, we're more than happy to have further discussions on this.
Okay, has anyone got any more questions?
I've got one more question in terms of the prepregs you've been using with this. Have you used or evaluated any of the interleaf toughened sort of prepregs with this manufacturing technique, and how did they process?
Yeah, that's don't know if Evangelos can help out. Are you talking about the types of the likes of M21 type things that Airbus might use?
Yeah, that's that sort of product, the M21 3900 types.
Have we, Evangelos?
Yes, we have, while we're still at the university, and I think there was a project that we were adding ourselves thermoplastic particles to improve forming, so to create like a lubrication layer between the preplug layers. But yeah, in terms of sealing and compatibility with our process, it's pretty much like standard preplug.
Okay. Thanks.
Yeah, and it's probably worth saying that we have developed a testing rig which allows us to evaluate any material. So we put it into this rig, and we can measure all the properties we need to know about, so that we can optimize the machine, and that will give us an answer about how good it will shear, how well it will shear. Yeah.
Okay, thank you.
Can I just ask one final question, unless anybody else has got anything to ask? In terms of finite element analysis, this makes it a little more complicated from my experience. We don't have constant angles in different layers. How complicated is it for finite element analysis to deal with these unusual fiber orientation distributions?
I'll take that, shall I?
Yeah, thanks,
That would
Andrew.
be good. Yeah.
Everyone else looking blank. Yes, it's a challenge, but actually we can still use the sort of the classical approaches. As you know, Chris, we're working on analyzing the fiber paths, so we're changing the fiber paths in the model and treating it as if it's a normal composite. The only slight issue is actually how it's going to fail going around corners. The other aspect, of course, is how do we design these things? You had an interesting example with a cone, but we want to try and make this so it's something that a designer can use easily. We don't want people with PhDs and so on being involved with every single design. We want to simplify it, and that's the whole process we're going through. Things like failure going around corners. We have a micro modeling approach which we could use to assess whether a particular failure mode is going to be influenced by really tight radii.
Thank you.
But yes, in the next year or so, hopefully we will have some production software which will help people design and analyze parts with this.
And I think this discussion illustrates the point that Dominic made earlier, that it's not only manufacturing, it's also design and testing. And that's basically where, to make this technology a reality, fiber steering a reality, we need to develop these capabilities within the supply chain. And I think the UK is positioned, very well in this area as a whole. So, we've got excellent R&D institutes and already excellent SMEs and large companies that can support this. So yeah, certainly I think the next couple of years will be really exciting in terms of capability development.
It's something certainly I've seen several times that new technologies basically get throttled by the lack of design capability. So certainly it's something that whenever we think of a new approach to make something, we've got to have the design software and analysis software to make sure it can be used in real life.